Good morning everyone. Welcome back to our lecture series on advanced hydraulics. As you know, we are in the 6th module. Today is the second lecture of this particular module on turbines. Today we will be going to take a portion related to pumps. For example, in the last class, if you recall them, we have briefly discussed on what is meant by turbo machine. So, you have remembered that turbo machine involves pumps and turbines and some other instruments as well. So, how the impact of high speed jet of water occurs on a flat? What is that impact due to a high speed jet of water hitting a flat plate? You have analyzed that, what is the force exerted. These things also we have seen it in the last class. We have applied the momentum principles to analyze the above situation both in flat plate and curved plates and all. Today one of the turbo machine which we are interested to analyze is pumps, because as I said in the previous lecture, if you go to the site, you may be required to investigate about the pump facilities there. So, or even as an engineer, when you have to go there and visit the things, even in irrigation sector, not only in hydropower sector, the pump facility, whether the pump design is sufficient for the extraction of water and all. So, some basic knowledge on pumps, that will be covered in this particular topic. Let me introduce about the pumps. So, pumps are the turbo machines that are used to extract or transmit any liquid from a source to another location. So to provide this thing, that is, if you want to transmit water, what is the thing required? You need to supply certain quantity of energy. You need to provide energy, and that energy will be utilized for transmitting water. For a simple steady state condition, if you apply energy equation between two sections, if you see that, then you will observe that the energy is added between. For example, I am just drawing a line diagram in such a way that you recall the steady state, mostly in our open channel hydraulics and all, we were able to apply Bernoulli's equation, that is, or the energy equation also, if you recall that, you are able to apply that. So, the Bernoulli's equation, what it was stating, if you remember them, if you take two sections, then the total hydraulic head or total energy head in both the sections, they will be same, or if there are losses, then that quantity also you need to take into account. In this particular situation, if I take, say, a line diagram, means where, so this is the section 1 at a particular location. You can envisage it as some maybe channel or maybe some water resource body and all. And another section is there too. Fine. So, water you need to extract, you need to so there will be some energy head at section 1, and that energy is not sufficient, means that is the natural energy. How do you write it? Write the energy head equation, if you recall them, that is, we used to write it pressure head plus velocity head plus datum head. Like this, we used to write the total energy head at any section. So, if this energy at this particular portion is given, similarly at section 2 also you can write appropriately the energy head. There will be, of course, if the flow is occurring from left to right, there could be some natural energy losses. If you take that also into account, that is fine. Now, This energy is not sufficient to draw water from a particular location. Suppose if you want to draw more water to some other location, what we have to do? In addition to this energy, you have to provide some external energy, and that some external energy del H will be provided between these two sections. So, an additional del H will be provided between these two sections, and you will get a modified energy at section 2. Fine. That is how energy is added into the system using a pump, and you are able to draw water. The reverse process occurs in turbines. So, let me give a classification of the pumps, a brief classification. There are mainly two basic types of pumps. They are the positive displacement pumps, or in short they are called PDPs. In many of the references you can see them being written PDPs and all positive, it is called positive displacement pump. And the second type is dynamic or momentum change pumps. So, what do you mean by positive displacement pumps? That is, positive displacement pump, what they do is that they extract water by a particular principle, that is, you use or you change volume of liquid at a certain location by a force. Using some force, they change the volume of the liquid and then subsequently transmit the water. This particular principle or is being suggested in positive displacement pumps. For example, if there is an inlet chamber, or if you have a cavity at the inlet location, that cavity, if let us consider that cavity in a cavity form, it is an enclosed cavity. If that cavity is now open to certain water location, wherever water is available, then fluid is allowed to enter into the inlet to the cavity. Once the water enters, the cavity gets closed. Now, inside that cavity, water starts getting rotated through some other mechanisms. You can provide some appropriate instruments like rotor mechanisms and all, and also it gets squeezed. The outlet of the cavity now opens and the water gushes out through that outlet. When it gushes out, it will be having more speed, more velocity. This is the principle behind the positive displacement pump. A very simple example and one of the highly quoted example is the heart of any animal or any human being. So, we can just give some classification of the positive displacement pumps. How the positive displacement pumps are classified? One of the first classification is reciprocating pumps. So, the reciprocating pumps consist of piston or plunger pumps. As the let me again reiterate here, our objective is not to go at a higher level in the turbo machinery or subjects and all. You can read any of the reference topics related to turbo machinery. There are many handbooks related to turbo machinery as well. You can read them and you can gain more knowledge. It will be appropriate. We will be here just briefly suggesting the terminologies that will be useful whenever you go to site or whenever you try to design certain aspects on hydropower sector or irrigation sector. So, the piston reciprocating pumps consist of piston or plunger pumps. It can be a diaphragm pump, then it can be, I am sorry here, it is wrongly typed, this particular, it is not dynamic. So, the piston or plunger pump consists of reciprocating pumps consist of piston or plunger pumps and diaphragm pumps. Then you can have another classification for positive displacement pump, that they are rotary pumps or single rotor pumps. You will be also in rotary pumps, you may see examples like sliding vane pumps, flexible tube pumps, screw pumps, peristaltic pumps. Okay. So, just see the figures. We have quoted this figure from the Tata McGraw-Hill published book Fluid Mechanics, authored by FMY. So, in that from the figures we can see the reciprocating just the portion of reciprocating cross section sectional views of the, it consists of liquid chambers, suction check valves, you can see here inlet means. So, the cavity portion is there, then it opens, then it rotates, then it gives the discharge at this location. Similarly, in the rotary pumps you can see sliding vane pumps. So, the vane slides, and due to the sliding it opens at one portion and closes at another portion, like that principles are there. Flexible tube pumps are there in rotary, single rotor rotary pumps and all. Like, so, such figures are taken. Now, rotary pumps can also include multiple rotors. Some of the figures are given here: external gear pump, then we have given another example of lobe pumps, screw pumps, circumferential piston pumps. Like these classifications are given, you can just note it down. So, as per the means you have double rotors here, you can see the two rotors here. In this also multiple rotors are there, double screw, double circumferential, 3 lobe pumps and all. So, we are not going to discuss on the design aspects of these machines. So, PDPs, as we suggested, in the positive displacement pump, the cavity opens and it allows water inside, then the cavity is closed, water gets rotated and squeezed, and the cavity door is open and water gushes out through that, right. That is the mechanism going on. So, in this case, the inlet and the outlet of the pump, it is not operating simultaneously. You are having that, it is some sort of a periodic state. An inlet will be open, it allows water, then it closes, then outlet opens. So, it involves some periodic mechanism. So, the flow from positive displacement pumps are usually periodic. This is because, as we suggested, the cavity volume opens, traps and rotate and squeeze the water before closing. In this mechanism, any type of fluid can be used for pumping, whether it is a low viscosity liquid or whether it is a high viscosity or even sludges in environmental. You can use the positive displacement pump for pumping those materials. But you need to take care, you cannot operate in every conditions the positive displacement pump. If the outlet of the pump gets closed due to some or other reason, then definitely you need to take care, because if the outlet gets closed, a huge pressure starts building up inside the motor, and this pressure, it can burst the entire machine and all, and you cannot directly operate then. So, you need certain types of valves to reduce the pressure or to release those pressure from appropriate places. So, that mechanism is required. So, you take those things into picture. Let us go into the next type of pumps. We suggested that there are two main classifications of pumps: positive displacement pumps and dynamic pumps. we will be discussing here on both the aspects. Now, briefly let me tell what is dynamic pump. The theory of this dynamic pump is based on the very simple concept of change in momentum. So, even in the last class you have studied for the vanes, if a high speed jet impacts a jet, that involves change in momentum, that will create force. So, that simple principle is being used, but here what we are going to do? We are now going to add momentum to the system. If you add further momentum to the system, definitely you are getting more force to those situations. So, more force is being created. So, that is the principle behind dynamic pumps. What are the types of dynamic pumps? It involves rotary pumps. Some of the rotary pumps are centrifugal pumps, axial flow pumps. So, please note as it centrifugal, you will be seeing that the centrifugal mechanisms are involved there. Axial flow, as the name suggests, there could be some long axis involved somewhere, and axial flow pumps means, so direct straight. You can have mixed centrifugal or it is also called radial flow. So, it can be radial flow. Here you can have mixed axial and radial flow combined. Such pumps are also available. Then the next type of dynamic pumps are specially designed pumps. These are most of the general things. Specially designed pumps like jet pumps are involved. We will briefly discuss them anyhow. Electromagnetic pumps, the simple principles of the electromagnetism is being involved there. You can use gas lift or hydraulic ram, and pumps are working on that hydraulic principles also. Such pumps are also available. So, dynamic pumps, they can extract and supply water at a higher rate compared to your positive displacement pump. Dynamic pumps can extract, means it can supply water at a faster rate. They have, means it has been recorded that through many analysis and all, it has been observed that. But the thing is that dynamic pumps require a mechanism called priming. What is that? That is, if gas is, means if you have a pump set for extracting water from a location, and if gas is being filled in some of the chambers, if gas happens to enter in those chambers and all, then you cannot directly use the dynamic pump for extracting fluid or water from the source. So, that way you need to remove that gas from the system before starting the operation of the pump. So, that mechanism is called priming. One of the most importantly used dynamic pumps is centrifugal pumps. So, we will first deal with the centrifugal pumps. So, what is meant by centrifugal pump and all? We will just have a brief discussion today on those aspects. So, the centrifugal pumps, they are a type of rotodynamic machines. It has an impeller that rotates in a casing, then fluid enters axially into the casing, the fluid rotates inside the casing in the direction of the blades of the impellers, and it moves forwards tangentially and radially into the diffuser of the pump. Then water is then transmitted through the diffuser into the outlet. So, usually the fluid gains velocity and pressure while passing through the pump. So, I can just give a brief sectional view of the centrifugal pump and all. So, as we mentioned, it is a type of rotodynamic machine. So, you can have the sectional view, say a casing is given here, it is connected with an inlet, and let us assume that this is as the casing, and it consists of impeller blades and all. So, let us assume a this shaded region where water cannot enter, or it is connected to a shaft, it rotates. So, the impeller has some sort of blades, like this blades and all. I will just show another sketch of the how the actual impeller and its blade look like that. So, here just let us assume that. So, this is the inlet portion, water will come inside like this, in this, it will come in this particular direction, then it will means along this it will hit the impeller blade, it is rotated through some source, through some other energy sources, you are rotating the impeller blades. So, water also gets rotated along with it, then it gets transmitted, it goes further into the diffuser portion of the pump, then from the pump diffuser portion it is transmitted to the outlet, like that the water is getting pumped. So, usually what happens is the fluid gains velocity and pressure while passing through the pump. So, we have suggested that in pumps you are adding energy to the system, whereas in turbines the energy is taken from the system. So, here through external sources, that is energy is added, and there will be an increase in velocity and pressure of water. So, thereby the purpose of pump is being suggested. So, here we have just given a sketch taken from F. M. White's Fluid Mechanics, published by Tata McGraw-Hill. So, there you can see a portion of impeller. This is how the impeller. So, in the inlet of the pump, wherever we have suggested this particular portion, it consists of such an impeller disc having impeller blades as shown here. Say there are various you can see curved impeller blades on that impeller disc. Okay. So, this is connected at the inlet. So, water comes and goes into the system like this. So, it will rotate. So, if the impeller blade is rotated, water starts rotating, then it goes tangentially as well as radially further into the chamber, other cavities and all. Then from there it is connected to a diffuser. From the diffuser the water is coming out like this, from the impeller portion it is coming, then it goes into the diffuser, it diffuses into the outlet chamber. So, this is how the impeller and diffuser portions looks in a motor, in a pump. So, you can see the blades. So, as we have already studied the vanes and all, you can clearly imagine when the water strikes these blades and all, you can use the same principles of vanes, means high speed jet hitting a vane and all. The same principles are applied here. So, the impeller blades, they are backward curve as shown here. The blades can be opened or closed, you can open or close appropriately. So, there is only a small passage available when the blades are opened. If you look into the previous figure slide and all, there will be only a small passage. So, from the inlet. So, you can go suggest now the centrifugal pump. Usually we analyze it with the following assumptions. We are first trying to suggest steady state conditions. The entire system is now in steady state condition. Then we neglect the effects of viscosity, we neglect the heat transfer mechanism. Then we are now going to apply Bernoulli's equation between sections 1 and 2. So, again I am just redrawing the portion. You have inlet here. Okay. So, for a better clarification, I can just give, say, let us consider this as section 1, and the section 2 will look more like this. You can have a circular disc having the impeller blades. Okay. So, you have already seen the picture of impeller. So, like this. So, it is mounted, this impeller blade is mounted in a casing, and the entire casing is then further extended. It will be connected to the diffuser portion, and from there it is being suggested to the outlet. So, this is your section 2. Like this, let us assume the situation now. So, here I can assume this as section 2, section 1. So, in the inlet the impeller blade is there, in the outlet after passing through the diffuser blade at the outlet you can assume it as a section 2. And it could be pipe or it could be any other water carrying source and all. We can apply the same Bernoulli's equation between sections 1 and 2. It is the famous, because we are already considering the conditions as steady state. So, you know that Bernoulli equation can be applied only in steady state conditions. So, the Bernoulli's equations will now be applied, that energy equation, total energy equation will be applied between sections 1 and 2. So, the total energy head at section 1, this can be given as, say, the pressure head plus velocity head plus datum head at section 1. Like this we can write it. Total energy head at section 2, this can be given as P by rho g plus the velocity head plus datum head at section 2. So, use these equations. So, head loss or total change in head from section 1 and 2. So, why I am writing it additionally like this is that you cannot claim it as head loss, right. In the pump you are supplying additional energy. So, you are gaining some energy. So, we can write it as total change in head from section 1 and section 2. So, that is del H. I can write it del H, this is nothing but equal to the quantities total head at section 2 minus total head at section 1, okay. And this is nothing but equal to HF minus HS minus HF. where HF is called the pump head, additional pump head supplied. This is the additional energy head you are going to supply through the pump. Sorry, it is not HF, it is HS. HF is the loss in head. Your head can get lost, say in various chambers, the casing volume is there, or it can get lost in some other means and all. So, you can easily suggest now. So, HF is the loss in head that can come into picture. So, we will be writing the total change in energy head as HF minus HF. So, if you look into this cross sectional view of the side sectional view of this particular casings of pump, you will see that the datum, it can be taken, means there will be very much less difference in the heights between two sections. So, it can be almost considered as negligible. If it is more or less than 1 meter and all, it can be considered negligible. Then what happens? The velocity, we are assuming steady state conditions, and moreover the velocity at section 1 and section 2, they may also be assumed same. Fine. So, if V1 average and V2 are assumed same, then what happens? You are having steady discharge in the conditions. Therefore, your change in head, this is nothing but equal to P2 minus P1 by rho g, that is equal to change in pressure head, or we can suggest whatever additional head you are providing, that is nothing but the change in pressure head. Okay. So, that way it is now easily understandable in the sense that the entire energy head, even though you supply energy head, although the total energy consists of pressure head, velocity head and datum head, the contributions or change in velocity head and datum head are negligible, and we consider the entire change in the energy head is reflected in the change in the pressure head of the system. So, what is the power? Means we can now go for power. So, power delivered to the fluid. What is the power delivered to the fluid by the pump now? This can be given as Pw. So, Pw is nothing but the products of specific weight of water or fluid, any fluid, the discharge, we have suggested that this is for a certain discharge. So, discharge into the net change in head, right. So, you just go to the previous portion, change in head is del H. So, that same thing will be taken here. So, specific weight into discharge into del H. So, this is the power intended to be delivered to the fluid by the pump. This power is called water hose power. So, that is, this is the power that is required or that is supposed to be delivered by the pump to the fluid, so that the fluid can gain so and so energy. So, that is the objective here. Now, what do you think? So, whether if the pump through some other source, if they use only this much of power, and if it is delivered, means whether the pump will be able to deliver this much amount of power to the fluid, is it possible? So, the power required to drive, so power required to drive a pump. So, the power required to drive a pump, it is called brake horse power. In certain books it is written bhp also. I will be using it as P bhp. So, that is this much amount of power you have to supply to the pump, then only the pump will be able to supply a power Pw to the fluid. So, what does that mean? Theoretically, pump requires more power and some of the energy is lost due to various losses and all, water losses and all. Subsequently, the amount of power transmitted to the fluid is Pw. 100% efficient pump, which is not practically possible, have 100% efficient pump have Pw is same as the power required to drive a pump. So, P bhp, but due to various losses you can easily suggest that usually Pw is less than P bhp. So, what is P bhp? How will you evaluate it? So, P bhp is usually given as the angular momentum into the torque of the shaft. Okay. So, the angular momentum into torque of the shaft, that is given as the power required to drive a pump. So, I can suggest it as shaft angular velocity. Tau can be given as the shaft torque. So, in our earlier lectures, some of the modules and all, we have used tau for shear stress. So, please do not confuse with the symbol here. Here the tau symbol is used to denote the torque of the system, torque of the shaft. So, as we mentioned, power delivered to the fluid is less than the power used to drive the pump. Therefore, we can devise an efficiency factor. So, eta, let us consider the efficiency factor. This is nothing but equal to Pw by Phb, where eta ranges from 0 less than eta less than 1. Eta is equal to Pw by Pbhp means this is rho q g del h by this is Bhp is omega tau. What should be a pump designer's aim? A pump designer's aim should be he should like to design a pump that is having a high value of eta. So, what are the various losses that can reduce the value of eta? What are the various losses that can reduce eta? So, you can think of the efficiency condition, that is eta, you know, it is efficiency factor. So, efficiency can be correlated with the volumetric condition of the system, volumetric conditions. It can be interpreted with the hydraulic conditions. It means it happens that that particular pump design is not hydraulically efficient. So, there may be considerable loss due to bad hydraulic design. So, that may also reduce the efficiency, right. The volumetric condition, another feature. Then the mechanical conditions. The volumetric efficiency. The volumetric efficiency, we can discuss it with the following terminology. Say we can give it as eta V now, subscript V. This is the discharge intended or the discharge from the pump. It is not intended, means that is the design value, right. So, we are taking discharge Q, Q by Q plus QL, where QL is the loss of fluid So, you might have seen several pump sets and all where some minor leaks are there, leakages or water is coming out from certain locations and all. So, they are all various types of leakages. So, there could be loss of fluid due to leakage. Q is the discharge, steady discharge from the pump. So, this is the volumetric efficiency relationship. Hydraulic efficiency. We can now correlate hydraulic efficiency, say by a factor eta h. This is nothing but 1 minus Hf by Hs. Can you recall these terms? Hf we suggested that loss in the total energy head due to various like friction and all. Hs is the energy supplied to the system, right. So, if the water system energy Hs is the energy supplied and energy head supplied to the system. So, there could be Hf can be of means Hf that is the losses can be of various nature. It can be due to shock, if some shock waves are generated or some shock is created, means abrupt interruption of water or some type of this thing that can create some loss. So, that is shock loss. Due to friction, there can be some loss in head, right, and due to circulation of water, there will be some loss in the energy head. So, these factors create loss in head, that is being termed as the or that is correlated with the hydraulic efficiency of the system. Mechanical efficiency. You can suggest now mechanical efficiency as say eta m. This is nothing but equal to 1 minus a power called P f by P BHP, where we are now suggesting P f is the power loss due to mechanical frictions in the bearing. Power loss due to mechanical friction in the bearings and mechanical systems. So, this is, see how it is getting differentiated now. You have seen the figure of impeller, diffuser and all. So, these are all mechanical devices. So, those mechanical equipments, if they means if when they are connected to the shaft and if that for rotating, if you require some ball bearing connections and all, due to those connections there could be friction loss. So, those friction loss will cause the loss in power, means whatever power we were interested to transmit to the water, some of them get reduced due to this mechanical equipment, means due to the connections of various mechanical equipments. So, that loss is now termed as mechanical loss, or the corresponding efficiency is termed as mechanical efficiency. So, you know that PBHP is the brake horsepower of the pump. So, your total efficiency, usually it is given as the product of these three quantities, eta V, eta hydraulic efficiency and eta mechanical efficiency. So, now what can you say now? We can just briefly go through the pump theory. Let us consider a one dimensional fluid flow in the pump system. One dimensional fluid flow in the pump system. Now, if you recall the Reynolds transport theorem and all, so if we are considering this as the entire pump portion as a system now, we can use the control volume theory. So, the entire pump is a control volume. Reynolds transport theorem, we can utilize them. Okay. So, in the Reynolds transport theorem, okay, just for your benefit I am again writing it. We have suggested the Reynolds transport theorem for any arbitrary quantity capital B or any arbitrary property B, which is an extensive property related to mass of the system. So, the material derivative of that quantity is nothing but the net amount of that extensive property generated within the system plus V dot n dA. So, that is this quantity is the net outflow or net net outflow of that extensive property to the control surfaces of the control volume, right. So, like this we have repeatedly, means we have seen for various cases this particular. The same thing you can now utilize here for these pumps also. So, here let us take angular momentum as the extensive property. So, let us take angular momentum as the extensive property. So, angular momentum, it is a vector, you can now suggest H as the angular momentum, fine. So, H is the quantity B in the above equation, and we have say angular momentum about any point O in the control volume. You can now suggest this as H O. This is this can be written as R cross V dm, that is we are suggesting it as an extensive property related to mass. So, you know that the quantity R cross V gives the angular momentum per unit mass. So, this quantity, if it is integrated with respect to the entire mass in that volume, so that will give you the angular momentum in that control volume, right. So, this is just to denote it as an extensive property. So, from this you will get the intensive property beta is nothing but equal to R cross V. So, therefore, your Reynolds transport theorem dHO by dt is nothing but equal to dou by dou t, the control volume integral volume R cross V rho du, that is du is the elemental volume of the control volume, that is for the integration, plus the controls of you are having areal integral R cross V rho V dot n dA. Just go to the previous slide, the same equation as specified here. For the angular momentum, we have suggested it now appropriately. Okay. So, as we suggested, the pump system is taken as one dimensional. We suggested that the pump system is taken as one dimensional. So, you have a definite radius, means inlet condition and definite outlet condition. So, all other directional control surfaces, they are not transmitting any flux. Also, we are considering steady state conditions. Okay. So, we can have dHO by dt now is equal to R cross V rho V dot n. See here, the velocity is given in the vectorial form. We have not averaged it to the cross section, means any sections and all, that is averaged only after integrating the thing, or we can take the average velocity into area appropriately and suggest the quantities. So, this is nothing but if the momentum or the areal correction factors, if they are negligible, you can just take these quantities now. This is nothing but R cross V at the outlet into what is rho V dot n dA at any particular section. Say if I am taking an arbitrary, say if this is the inlet portion. So, this is the area, right. So, this particular area you are integrating. So, rho V dot n dA, you can now say write the same quantity as n is outward vector, unit outward vector from this surface. So, V. So, V dot n will give you the magnitude or the velocity, right, appropriate to that plane, So, V dot n will give you, so V dot n into dA will give you the discharge quantity, right, through that inlet. So, discharge into rho, what is that quantity? It will be the rate of mass coming in or going out. So, I can suggest now this quantity as m dot, that is rate of mass going out, to m dot out minus sigma R cross V inlet at the inlet. Fine. So, like this I can now write the for the one dimensional case. So, what is this momentum angular momentum theory suggest? Angular momentum theory suggests the material derivative of angular momentum is nothing but the sum of moments of all forces acting at the arbitrary point O in the control volume. This is the theory behind the angular momentum. So, that theory we will be incorporating it here. So, we can, that is the sigma m o is the net moment of all forces at point O. We can suggest net moment of all forces acting at the point O, right. Incorporate the same phenomenon now. So, we will be applying the same angular momentum theory for the blade impellers as well as the diffusers in the pumps. In the next class we will demonstrate or we will go through how, say, if you can devise a, say this is the, you have already seen the impeller disc. So, your impeller, I can just redraw the thing. So, it consists of inner radius and outer radius. The impeller blade can be in the curved form like this, right. So, water when it hits here, then it gets transmitted like this, then it goes out from here, right. It can go out, it goes like this. This is how the impellers work. So, the same thing we will now discuss on the we will discuss how to apply the momentum theory, angular momentum theory on that, and we will work out on the theories and efficiencies related to pump. Thank you.